welcome. It's amazing to see so many people. So I'm Simon Moore. Actually going to just start, it's sort of interesting, you know, we've already hinted that the department was founded on building computers. So why are we launching a computer architecture centre now? And perhaps if I give slightly my perspective on this, you know, in the very early days, they were just trying to figure out how to build things. There was no industry, and it was a great opportunity to really innovate. And I'm going to tell you a little bit about the CAP computer in a minute from the early 1970s. But really, sort of after the 1970s, in terms of microprocessor work, it pretty much stopped in Cambridge. There's a lot of work on networks and on building systems, a huge amount of systems and networking work. I came here in the 1990s to do a PhD and looking at multi-threaded processors and things. And I have to admit, I was getting a bit cheesed off with this. And I remember talking to Chuck Thacker, who was involved in setting up Microsoft Research. And, you know, Chuck had done the amazing work at Xerox PARC, inventing, you know, machines with windows and icons and mice and all sorts of things. And he was telling me, it's okay, it's going to look good in the future, you know, keep going, which was great encouragement at the time. And really sort of, I was appointed as on the staff in '98, and just a sort of couple of years after, Rob and I sort of decided, well, we should probably have a computer architecture group. So there was just the two of us. And as we sort of said at the time, it was a bit of a toy group, really. It was a bit of a joke in a way. So you can't really have a group with just two people. So anyway, we started going and doing all sorts of wacky stuff around self-time circuits and neuromorphic computing. Did some work with Steve Ferber on that, and also networks on chip. And there have subsequently been so many people involved. I realize I've now graduated 27 PhD students. But I thought I'd just call out to a couple of people because they're in the audience, but also to indicate some of the things that we're doing on the time. So there's one PhD thesis, Exploring Networks on Chip for FPGAs by one Rosemary Francis, who's up there. And I'm delighted to say Rosemary, I always think this is a great idea, actually, and industry didn't end up using it, but Rosemary went off, set up her own company, sold it to Altair, and she's now chief scientist. And I'm delighted to hear she was made a fellow of the Royal Academy of Engineering just a few weeks ago. She's just amazing news. I'm so proud. And sitting right next to her, because he's not going to get away, was one Dan Greenfield. So this is Communication, Locality and Computation, Software, Chip Multiprocessors and Brains, which was linking to, and it was really fascinating work, actually, looking at how communication fundamentally scales. And it really did some interesting work, actually, with mammalian brains and working with with people in that discipline. Anyway, Dan won the UK Distinguished Dissertation Prize, the top PhD thesis in the country in computer science in 2011. So that's pretty amazing. But actually, that sort of ties in. I think, you know, we're not interested in computer architecture just from the point of view, how do you build a processor? But I think we're all of us involved. Tim then really got involved very early on. We started growing the group, you know, more recently hired Prakash and Tobias. But also, critically, people like Robert Watson really joined in the group. Robert's nominally in security, but has really been leading the CHERI work that I'm going to tell you about. And also people like Peter Sewell, who does a lot of work on programming languages and verification. He's done a lot of work on verification, and that's been pivotal to this project, so he's listed on the list. And then we've worked with people in the States, so Peter Neumann, who's now in his 90s, would you believe, and Brooks Davies at SOI International. So many, many people involved, and it's great to see that, you know, we're sort of growing a team. And I think it's a great opportunity for, you know, Tim's launching this Computer Architecture Research Centre. So I think it's a great time to do that. And also, hooking back to the technology, it's, as Rob alluded to, industry's got many challenges at this point. So it is really a golden time to do computer architecture. Whereas I was getting a little bit frustrated in the 1990s, I think, you know, early 2000s, it was becoming clear that there were going to be problems ahead. You know, Dinard scaling sort of stopped around 2006, and, you know, we're seeing many, many challenges ahead. And I always think it's fascinating when you start looking at what industry is doing and thinking, that's mad. Why are they doing that? And if you look at modern superscalar processors, they're doing everything possible to extract as much instruction level parallelism as possible. And you look at the amount of power and the number of transistors involved trying to do this, and you think, that is absolutely crazy. Should never be doing that. And I always think this is a great start for doing computer architecture. Anyway, this leads me on to this talk, so I should get on with the talk properly. CHERI, really, so looking at how do we fundamentally improve security is also looking at one of those problems where it's nuts. Why isn't the industry doing better? And the thing that's nuts is we see that the number of vulnerabilities reported just keeps growing. It's just getting worse. And there are many challenges around this, which I think I will allude to as we're going through, otherwise I'll never get through my slides. So, quick historical perspective. Obviously, our own machine, EDSAC, you know, in 1949, you know, they had the simple idea of linear physical address space, and I don't know how many of you have gone and read the early work in the US, you know, the first draft report on ENIAC by von Neumann. Because if you haven't read it, I recommend it. And von Neumann, who's a mathematician, had really been working with these engineers. And one of the things that's kind of nice with that report is he looks at a design space and he starts saying, well, we could have addressable memory. And we could store everything in addressable memory. But we kind of need a scratch pad of some sort. And he starts thinking about, well, what might something like a register file look like? And so on, he starts building it up. But the funny thing is, some of the basics, like linear addressable memory, is still very much with us today, although, of course, we do virtualize that to some extent. Back in 49, even things like the subroutine had not been invented. So Alistair talked about David Wheeler's PhD thesis, probably could well be the first PhD thesis in computer science. And in that thesis, he invents the subroutine, and in particular, the mechanism. So EDSAC didn't have a mechanism to jump to a subroutine and then return. He invented something that involved self-modifying code because it was the only way you could do it. But that's also interesting, and it started making you think, you know, thinking about that hardware-software divide, what are the things that we want to really support software and systems in our hardware? And so often that interface between hardware and software, people do not do global engineering optimization across that boundary. People tend to either stick with the ISA and do all the microarchitecture underneath, or they're trying to, you know, compile and map things to that ISA. But I would conjecture you really need to explore both sides and do a global optimization. So EDSAC didn't even have virtual memory. That came later with things like the Atlas machine, which was from Ferranti, and Cambridge, in fact, you know, picking up on this theme at this point, starting to use more commercial systems. They couldn't actually afford an Atlas at the time, but worked with Ferranti, took some of the components, and built a machine called Titan. Right, let's talk about capabilities. So concept from the 1960s, this idea of object capabilities, and it's really an abstract idea. And the fundamental idea is a capability is an unforgeable token of authority. Okay? And people played around with these ideas. There were lots of machines, including the CAP computer, the 1970s, which is actually out in the street. You can go and have a look at it. And they're trying to figure out how to do, you know, what was this interplay between hardware and software? And I think many people don't even remember. And in fact, I've been to the Intel Museum in San Jose, and I remember going years ago, and they actually had the IAPX 432 mentioned in a little corner in the museum. And I went just a few years ago, and it's been expunged from the museum. It's as though this is something that never existed. But their very first 32-bit processor was a capability machine. nothing like CHERI, which I'm going to tell you about. It was a 3-chip monstrosity, really too expensive, too complicated. But it's interesting looking back at some of these old machines. So there's the cap. Excuse the model. I wanted to give a bit of a sense of scale. You can go and have a look at that. So the basic idea with the cap capability was you have these memory capabilities which have permissions, base, and limit. The program is allocated a set of capabilities, and the hardware can cache up to 64 of them. And interestingly, it had this notion that, the piece of code was given a set of capabilities, and then it used addresses, and then you had to sort of search to see whether you got permission to access that memory. All a little bit complicated. In the end, really, and I remember talking to Maurice Wilkes about this, virtual memory was a bit simpler, wasn't nearly as sophisticated as the capability systems, but it kind of won out. I think, the simplicity won. Okay, so that brings us to CHERI. So really, a modern look at capability architectures, and in particular the memory capability. So why look at memory capabilities now? What motivates this? Let me just have a quick drink. So coming back to this madness that we have ever more vulnerabilities in our systems, what's the root of a lot of those vulnerabilities? Well, here's a couple of quotes. One from Ian Levy, who's now at Amazon, but was director at NCSE. Buffer overflows have not objectively gone down in the last 40 years. The impact of buffer overflows have, if anything, gone up. Similarly, Matt Miller from Microsoft's Response Center, he estimated that from 2006 to 2018, given he was talking in 2019, year after year, about 70% of all the vulnerabilities were all memory safety related. That's kind of nuts. It's not just a Microsoft thing. We see the same thing out of Google with Chrome. There again, they're saying 70% all vulnerabilities, and they're just not quashing them. So more recently, we're seeing directives coming out of government, particularly in the US. So this is from NSA around memory safety and what needs to be done. There's also been a joint report last year looking at how do we shift the balance of cybersecurity risk. What are the new principles and approaches for security by design and default? And nicely, on the hardware side, they said, there's this thing, CHERI, you should probably use that, which is pretty neat. And there was a White House report from February, and there again, CHERI gets a mention as an example technology that can fundamentally improve things. So I keep telling you about this CHERI, what the heck is it? And how do we do better? How do we, rather than doing what we do at the moment to just keep on patching all these vulnerabilities, and we're clearly not winning that battle, how can we really get to the root cause of the problem? Well, one answer is you can use memory-safe languages like Rust, which I would argue is great for new code. Absolutely encourage people to use Rust. Brilliant thing to do. But it's really impractical to port the vast body of legacy code. And there are also issues around unsafe Rust. So even things like string libraries, the string library in Rust is written in the unsafe subset of Rust. And that makes me rather nervous. Our approach, on the other hand, is to take any language, but particularly we've been focusing on C and C++, basically on the basis if you can make it work for C and C++, which tend to do all sorts of grubby things with hardware, you can make it work for anything. So here we want to recompile your code and enhance the processor as a target to allow you to very efficiently, dynamically check all the memory accesses. And it can also make unsafe Rust safer. Interestingly, at this point, because we've been going at this since 2010, there's now more lines of C and C++ code ported to be completely memory safe than exist lines of open source, I should have added the open source, but lines of open source code on GitHub. We don't know about the closed stuff, and I'm sure there's lots of Rust code in, closed repositories, but in terms of what's in the open, yeah, we've ported a lot more code. So how does CHERI work? Well, rather than having this notion of a set of capabilities and then separately having memory references, which is what CAP did, we've really sort of merged the things together. So we replace pointers with this new data type. It's a bit like adding floating point, in a way. And the basic idea is very simple, but the consequences are quite profound. So we have a virtual address that is 64 bits. We've got compressed bounds relative to that address. We've got some other permissions and other bits of metadata, and critically, a 1-bit validity tag that is hidden. And that is absolutely critical to the security argument. So there's no crypto involved at all, but that validity tag and how that, when it's preserved and when it's cleared, is absolutely critical to the security properties. Okay? So using CHERI capabilities, we can guarantee integrity and provenance of memory references. The bounds make sure we don't mix up, heaps and globals, etc. We also have this very important monotonicity property. So if a piece of software has access to a capability, it can't grow its bounds. You can't gain the permissions. And in fact, that's a very critical security property, and one where we've actually done a huge amount of work. In particular, Peter Sewell's group has done full instruction set verification work. Basically, you want to do an inductive proof that says you cannot possibly construct a program that will violate this property, including dealing with exceptions and interrupts. And so they've done some pretty amazing work around that. Permissions, pretty obvious. Make sure you don't mix up read, write, execute, and so on. These are absolutely critical basis for doing very strong spatial memory safety. We can also use it for temporal memory safety, but that's another story. But also compartmentalization. So the other challenge we have when we build software these days is we're reliant on using huge libraries. And this is great. It really allows us to construct code more quickly, make use of accelerators and so on. Absolutely superb. But from an attacker's point of view, this is great, because the attack surface just keeps getting bigger. And all of those libraries are things that the attacker knows about. If you're doing, a return-oriented programming attack, or, ROP or JOP type attacks, this huge code base that you can see, you can start stitching together bits of code through various forms of remote execution to, attack systems. One of the great things about compartmentalization, which is a really fundamental idea, is that you break code up into smaller compartments. You make it very clear what the entry and exit points are from those compartments, and you give it very clear idea of what permissions and rights that compartment has. And so to give you a very simple example, if you've got a web browser, so shown here, you might have downloaded an image you don't know what it is, it's going to hit your browser, and that'll probably get, uncompressed using libpng. Well, there have been many, many vulnerabilities, including execute vulnerabilities in libpng. The thing that's nuts about current systems is we typically run libpng just with the ambient privileges of the user. So whatever privileges the application gets, that library gets as well. This is nuts, right? Because all you want that decompression library to do is take something basically in one buffer and decompress it into another buffer. It shouldn't call the OS. It shouldn't access any other sorts of memory. It's very easy, actually, with CHERI to just wrap libraries like this and just constrain what they do. And that really fundamentally improves performance. Now, at the moment, we don't do this because, well, we do it to a limited extent. So something like the Chrome browser, each tab runs in a separate process until you start getting too much pressure on the virtual memory system, in which case they start sharing compartments. But we can take this orders of magnitude further. But we do have a little bit of a chicken and egg problem here. CHERI gives you enormous speed-ups over process-based compartmentalization, but people don't do a lot of compartmentalization because it's so inefficient. So, yeah, that's an interesting one to sell. So, bridging the commercial chasm. So we started off 2010, working out all the principles, building little prototypes. Fairly early on, I will go in my bag of props. I should have probably put this outside. So there was basically an FPGA board with a battery and a display on it. So it's like an exploded tablet, really. But we sort of packaged it up. We had a lot of DARPA funding, and we wanted things to hoik round to demo to people, which turned out to be quite effective. So, you know, we've done all this stuff. And, you know, you built all the simulations, and we started showing it to industry. In fact, we started working with ARM, actually in 2014. Got kind of lucky. Started talking to Richard Grissenthwaite, their chief architect. One of the things he told me is, basically, FPGA implementations and simulations basically convince people who are already convinced. And it's like, oh, okay. So what are we going to do? So we ended up working with them and setting up an Innovate UK initiative, which is still rolling at the moment, called Digital Security by Design, to build a prototype platform and then get a lot of industry using it. So then we've got a Morello board, and here, another prop, have one of the chips. Well, actually, that's the chip, that's the package. So 7 nanometer chip. And this is a big deal, right? I mean, just a set of masks for a 7 nanometer process is $10 million. So it's kind of hard to do that. But anyway, managed to get that together. And that's been thrown over the wall to all sorts of people, and they've, you know, given us amazingly good feedback. In fact, we're basically at the point now where a lot of people in the industry says, we just want to buy hardware with CHERI in it. And we're trying to get over that hump at the moment. Giving you an example, there was a little study done by Capabilities Limited where they took 6 million lines of C and C++ code, you know, for desktop applications using a Unix type environment, recompiled all that code, and they found they needed to modify 0.026 lines of code. And this is typically doing things like getting rid of the custom memory allocators and things that are not CHERI aware. Also got very high mitigation rates for known past vulnerabilities in this code. We've got open source stack, so completely with Rob. It's great to do things in the open. In fact, we have one of the things I should have mentioned here. We have a very unique IP arrangement with ARM, this sort of capability essential IP agreement. Because we realized, basically, I'm after world domination. I want this everywhere on every platform, not just on ARM. I very much want to see it on ARM. But they also realized if we're going to take a lot of government money, the IP had to be available. We couldn't just have it, you know, they couldn't be seen to be just propping up industry, basically. Okay, so we've got open source stack, and it really is a stack. So I've been talking a lot about hardware, and we've done various implementations in FPGA, you know, little microcontrollers, scalar cores, but also we've got a super scalar core. But then there's a huge amount of work on, you know, operating system work, Clang LLVM toolchain, vast amount of work there. Some work on simulators. Peter Sewell has led the work on SAIL, which is a formal model of the instruction set for which we've got a version of SAIL for ARM, but we've also got one for RISC-V, and that's been upstreamed to the RISC-V International, is now their golden model in the RISC-V space. So a huge amount of work done there. We've thrown it over the wall to people like Microsoft, and they did quite a detailed study, 42-page report. They looked at all of their 2019 vulnerabilities, and the conclusion is that if they'd compiled their code using CHERI, they're pretty confident it would have mitigated 2/3 of all the vulnerabilities they saw. That has real economic impact because patching vulnerabilities comes at a lot of cost and a lot of risk. So, you know, it was a really exciting result. And that was also a very high bar, because they were saying, you know, it would have mitigated it to the point where they wouldn't have even bothered issuing a patch. It's like, you know, the vulnerability's just gone away. They also, so actually partly some of our team here went to Microsoft Research, and led by David Chisnell, they developed the system called CHERI, which is actually taking the low-risk IBEX core, adding CHERI support to it for embedded systems. Very interesting results out of that. Just demonstrates how efficient CHERI is even in that space. And also linking back to low risk, and in fact there's an example board just outside. They have a little FPGA board that is a demonstrator for CHERI that people can buy. In fact, I'm not sure if it's on Mouse yet, but it will be soon. And we have Carl from CoderSIP here today, and possibly a couple of others. We've been working with many people at CoderSIP, and they have announced a commercial 64-bit CHERI RISC-V core. And we're doing a lot to standardize things. So I'm saying a lot about RISC-V, but I really want this on ARM as well. We've done a vast amount of work with ARM. As I said, we want it everywhere. So in summary, because I'm running out of time. So what does CHERI give you? Well, it gives you deterministic, non-bypassable memory safety, both spatial and temporal. It gives you very high performance, very scalable compartmentalization. And it's very easy to adopt. We see that a vast amount of code, you just recompile it. The code doesn't look any different until you start to attack it, or you've got a bug. We often find bugs in systems. Even things like recompiling TC shell. You know, if you just do tab to do history compilation in a shell, we discovered there's a buffer underflow error in TC shell, which we think has been there for 20 odd years. It's benign, but you know. On the architecture level, we've got very detailed descriptions for ARM and for RISC-V, and we've got quite a detailed outline for x86. And then the microarchitectural level, sort of what I do, you know, we've demonstrated that you really can implement this. We've worked with the ARM engineers to do this 7-nanometer chip. So this is a superscalar chip. This is a Neoverse N1, which is used in the Graviton series of chips for AWS. So we know it can be built, and we've got a huge amount of software support. I mean, Robert's been leading all the work on the software side, and you need all of that software support. Absolutely critical to make use of CHERI. Because in many ways, CHERI at the hardware level is really quite simple. What gets really interesting is all the things you can build on top of it. Okay, so to conclude, I think CHERI is just a good example of research tackling a market failure. You know, disruptive and long-term research, these are both very hard for industry, but I think are really needed to make fundamental changes. You know, industry is much more willing to do incremental changes, but if you discover you're in a point where, you know, the systems are not, you know, you're having problems like major security problems, or we're seeing on superscalar processors, we're sort of running out of steam on what you can do to get more performance, and it's just burning a lot of power, and, you know, it's kind of nuts. You've really got to rethink what you're doing. The department's a great place to do work. I think, you know, from the very early days all the way through. I mean, Andy's here. Everybody's been, all the heads of the department have always encouraged people to work across research groups and to work in teams, and I think that's absolutely critical for tackling these problems. You know, it's not stovepiped around one professor. And finally, you know, if you want to do hardware, software, code design, it requires a big effort. You know, you need a lot of people. CHERI so far, in fact, I really must run the numbers more accurately, but I think we're over 200 person years of effort at this point, including, I think there's at least 12 PhD theses have come out of it. There's a lot of details to sort out. And actually, just to get this chip out of the door, ARM put around 100 engineers on it for 15 months. So, you know, big amount of effort to get this stuff done. And that's why we're looking at ways of funding things, bringing more people through so that we can do this sort of research. And with that, I better finish because I'm out of time. Thank you.
I think we could probably take one question. Please.
Oh, okay. So I'm old, so I can be cynical. When I look at a lot of the vulnerabilities that are, shown around, I look at them and I think to myself, yeah, well, okay, you could probably do that, but what's the point? Do you think we've got ourselves into a point where too many people are reporting vulnerabilities just because it's become a bit of a game? And it seems to me that there's a real problem in being able to zero in and say what are the ones that are the real risk, and how do we actually do that?
It's an interesting question. So the question's around, I guess part of the question is to what extent are these vulnerabilities a problem? And maybe another way of paraphrasing your question. I think there are fundamental problems, and you just got to look at organisations that have been taken out by vulnerabilities. And sometimes it is down to, human error and configuration problems, British Library. But, there are plenty of other examples. If you just look at something like the Chromium browser, a lot of us use a web browser. There are real risks. If you're doing banking stuff in one tab and you're doing stuff in another tab, they really don't want them to communicate. And yet, you look on Chromium these days, they are shipping bug patches, about every 3 days? And a lot of those are quite severe vulnerabilities, and they're finding them at that rate, and it's just not slowing up. So yeah, I do think we do need to fundamentally rethink. And actually, I'll share a quick fear. Sorry, I'm going on slightly too long. I put this as a challenge to you. If you look in other areas, say if we take something like genetically modified foods, Monsanto really messed up in the UK, and you ask somebody in the UK, would you eat GM food? They will say, absolutely not. And yet there is GM food now on the market in the UK, but it's very much under the radar. One of the things that worries me in computer science is if we are complacent, it's going to really hit areas like medicine, for instance. If we start losing a lot of medical data and then there are legal cases and people say, we want out-tack clauses if you're using our data for research and so on, people will start opting out and it'll just hurt science. Okay? And there are many other areas where computers are now being used in the consumer space. I've worked in aerospace where I know it's safety critical, but in the consumer space, we're becoming so dependent on it. And I think we should demand a higher level of engineering. So even if you think something like, I remember when Nest thermostats first came out, California product, I remember being out in California, early days, the servers went down, people's thermostats didn't turn on. California, it's not a problem, okay? If you're in the north of Scotland in the middle of winter and it's an elderly person, quite literally you can kill somebody, okay? So I think we have to step up as engineers and deliver much higher quality products. So no, I think we do need to take it seriously. So it touches a bit of a nerve.
I think given the time, we're going to stop there, but we've got a coffee break now, so everybody can come and talk to Simon then, and I'm sure he'll answer all your questions. Thank you.